You all are welcome once again to the class of Geotechnical Engineering 1. In the preceding chapter, which was Principle of Effective Stress, we considered some simple cases for which direct application of Darcy laws was required to calculate the flow of water through soil. In many instances, the flow of water through soil is not in one direction only, nor it is uniform over the entire area. In such cases, the groundwater flow is generally calculated by the use of graphs, which is known as flow nets. The concept of the flow net is based on the Laplace equation of continuity, which governs the steady flow condition for a given point in the soil mass. In the following sections of this chapter, the derivation of Laplace equation of continuity will be presented along with its application to seepage problems. The three-dimensional flow is the most general flow situation, but the analysis of such problem is too complex. Hence, flow situations are simplified to the two-dimensional flow. There are some assumptions which are made for the analysis. The soil mass is fully saturated and Darcy law is valid. The soil mass is homogeneous and isotropic. Both the component of the soil mass, that is soil grains and pore fluid, are incompressible. And flow condition do not change with time, that is steady state condition exist. To derive the Laplace differential equation of continuity, let us consider a situation where a single row of sheet pile has been driven into a permeable soil layer as shown in figure. The row of sheet pile is assumed to be impervious. Sheet pile is a type of a structure which is used to retain water on its one side. Let us consider an elemental soil block A, which is shown in an enlarged scale in adjacent figure. The block has a dimension dx, dy and dz. Length dy is perpendicular to the plane of paper. For soil block A, assume Vx and Vz be the component of discharge velocity in the horizontal and vertical direction respectively, and Ix and Iz is the hydraulic gradient in the horizontal and vertical direction respectively. Since we are considering the flow is a two-dimensional flow, so here velocity in the y direction can be taken as 0. Here the rate of flow of water entering into the element from the horizontal direction will be Vx into dz into dy, and from the vertical direction will be Vz into dx into dy, and the rate of outflow of water from the block in the horizontal and vertical direction are Vx plus del Vx by del x into dx into dz dy, and Vz plus del Vz divided by del z into dz into dx dy respectively. Since we have assumed that flow is steady, and in steady state flow there can be no volume changes in any condition with time, that is, there will be neither storage nor depletion with time in the amount of water contained in the pores of the soil element. So amount of water entering the element must be equal to the amount of water passing out of the element. After equating the rate of outflow of water with the rate of inflow of water in soil block and solving the equation further, we will get del Vx divided by del x plus del Vz by del z equal to 0. This equation represents the continuity condition for two-dimensional flow under a steady state flow condition. From the Darcy law, we can write velocity v is equal to ki. Now here Vx will be kx into Ix, which can be further written as kx into del h by del x, where h is the head causing flow. Similarly, Vz can be written as kz into del h by del z. Again, assuming that the soil is homogeneous, that is kx and kz are unique value and are not function of x and z respectively. And from the isotropic assumption, we can write permeability in all direction will be same, means kx is equal to kz. After substituting the above three values in the equation of continuity condition, we get del square h by del x square plus del square h by del z square is equal to 0. This equation is a partial differential equation called the Laplace equation for the two-dimensional flow. Since the Laplace equation is a partial differential equation, so the general solution of this equation yields two sets of curves which are orthogonal to each other. One set of curves is known as flow lines and the other set of curves is known as equipotential lines. A flow line is a line along which a water particle travels in its course of seepage through a saturated soil mass. In this figure, a flow line can be seen along which water particle travels from upstream to the downstream side in the permeable soil medium. On the other side, an equipotential line is a line along which the potential head at all points are equal. In this figure, dotted line is an equipotential line. If piezometer are placed at any points along an equipotential line, the water level will rise to the same elevation in all of them. That is, potential head will be same at each point of the equipotential line. The network of such flow lines and equipotential lines intersecting at right angles to each other is called flow net. Flow nets are constructed for the calculation of groundwater flow and the evaluation of heads in the media. To complete the graphic construction of a flow net, one must draw the flow line and equipotential line in such a way that the equipotential lines intersect the flow lines at right angles. The flow elements formed are approximate squares. To draw a flow net, it takes several tries. While constructing the flow net, one must keep some boundary condition in mind. To draw the flow net as shown in figure, there are four boundary conditions. The first boundary condition is the upstream and the downstream surface of the soil layer, that is lines AB and CD, are equipotential line because at every points of line AB and CD the potential head is constant. The next boundary condition is all the flow lines intersect the surface AB and CD at right angle because line AB and CD are equipotential lines. The next boundary condition is from point A, water flows down the seed pile on the upstream side, touches the tip of the seed pile E and moves up on the downstream face EC. Thus, AEC is a flow line. And the last boundary condition to draw this flow net is surface FG is a flow line because the soil strata beneath the line FG is an impermeable stratum. So water cannot penetrate this layer. So water only flow along the impermeable surface line FG. There are some properties of flow nets which are flow lines and equipotential lines are orthogonal to each other. That is, they intersect each other at right angle. The areas bounded by the flow lines and equipotential line form approximate squares. This figure is a part of flow net. As per the property of flow net, each flow channel in the figure will be approximate in a square shape. Flow nets must satisfy the boundary condition of flow field. quantity of water flowing through each flow channel is the same. That is, the discharge in field 1 will be same as discharge in field 2. The potential drop in any two consecutive equal potential line is same. Means potential drop in field 2 and potential drop in field 3 in this figure will be same. Flow lines and equal potential lines are smooth curves. Flow lines do show refraction at the interface between two soils having different coefficient of permeability. There are many methods that are in use for the construction of flow nets. Some of the important methods are analytical method, electrical flow analogy, capillary flow analogy, sand model, graphical model. Flow nets are constructed for several purposes, like to estimate the seepage losses from reservoirs, to determine the uplift pressure below dams. Flow nets are also important for checking the possibility of piping beneath the dams. Now, to derive the seepage formula, let us consider a part of flow net as shown in figure. Consider three fields 1, 2 and 3 in such a way that field 1 and 2 lies between two successive flow lines and fields 2 and 3 lies within the same equipotential line. The average dimension of the field 1, 2 and 3 are B1A1, B2A2 and B3A3 respectively. Let del Q1, del Q2 and del Q3 be the rate of flow through field 1, 2 and 3 respectively, and del H1, del H2 and del H3 be the head loss across the field 1, 2 and 3. Consider the width of the flow field in perpendicular to the plane as unity. From Darcy law we can write the rate of flow Q is equal to KIA. Substituting the value of I and A in the equation, we will get del Q1, del Q2 and del Q3 as written here. Since the field 1 and 2 are within the same flow channel, so we can say del Q1 will be same as del Q2. Also, field 2 and 3 are within the same equal potential line, so head loss through both the fields will be same, that is del S2 will be same as del S3. Further, from one of the properties of flow net, which is the area bounded by the flow lines and equal potential line form approximate a square. So we can write A1 by B1 is equal to A2 by B2 is equal to A3 by B3, which is equal to 1. Combining all these equations, we get del Q1 is equal to del Q2 is equal to del Q3 and del H1 is equal to del H2 is equal to del H3. That is, in a flow net, the quantity of flow through each field will be equal and head loss across each field will also be equal. Thus, we can say del Q is equal to K into del H. If capital H is the total head loss during the flow and ND is the number of equal potential drops, then del H can be written as capital H by ND. If the number of flow channels in a flow net is NF, the rate of flow Q through all the flow channels per unit length is given as Q is equal to del Q into NF. Substituting the value of del Q, we get rate of flow Q is equal to K into H into NF by ND. This equation tells that the rate of flow is a function of permeability K, loss of head H and NF by ND ratio, which is called the shape factor. Sometimes it is not necessary to make all the fields elementary squares in a flow net. It is only necessary to make A by B ratio the same for all the fields. If A by B is equal to N, then Q can be written as K into H into NF by ND into small n. Flow nets can also be used in calculating the uplift pressure under masonry dams. Water that seeps below masonry dams or weirs founded on permeable soil exert pressure on the bases of structures. These pressures are called uplift pressures. The diagram of distribution of uplift pressure along the base of the dam can be drawn, and the total uplift force then calculated by working out the area of the uplift pressure distribution diagram. Since uplift pressure acts vertically upward, that is against the gravity, it reduces the stability of the hydraulic structure. So it becomes necessary that the uplift pressure should not be allowed to go beyond the permissible limit. Uplift pressure along the base of machinery dams can be effectively reduced by providing vertical cutoff walls at the upstream end of the base of the dam. Consider a weir founded at a permeable foundation at a depth 2 meter below the ground surface. The depth of the water on the upstream side is 7 meter and on the downstream side is 0. So the head difference between upstream and downstream will be 7 meter. In this figure, water flows from the upstream to the downstream side. From the flow net, it can be seen that there are 7 equipotential drops. So the head loss for each potential drop can be calculated as total head by number of equipotential drop, that is 7 by 7, which is equal to 1 meter. The uplift pressure at any point is equal to the pressure head at that point into unit weight of water. In this figure, pressure head at point A will be the height of water at that point minus the head loss. At point A, the total head is 7 plus 2 meter, that is 9 meter. And head loss will be head loss for each potential drop multiply with the number of potential drop up to point A. So here head loss will be 1 into 1, that is 1 meter for point A. So the pressure head at point A will be 7 plus 2 minus 1, that is 8 meter. Therefore uplift pressure at A is equal to 8 gamma W. Similarly, the pressure head at point B is equal to 7 plus 2 minus 2, that is 7 meter. Since the number of potential drop to reach point B is 2. So uplift pressure at B will be 7 gamma W. Similarly, the uplift pressure at F will be 3 gamma W. After calculating the uplift pressure at different points, the uplift pressure diagram can be plotted. And the area of that pressure diagram tells about the uplift force per unit length measured along the axis of the weir. Apart from uplift pressure, exit gradient can also be calculated from the flow net. The exit gradient is the hydraulic gradient at the downstream end of the flow line, where percolating water leaves the soil masses and emerges into the free water at the downstream. The exit gradient should always be less than critical hydraulic gradient to avoid piping or boiling condition. Exit gradient can be reduced to a considerable extent by providing vertical cutoff walls at the downstream end of the base of the dam. The possibility of piping which occurs during seepage is more in regions where the flow is concentrated and seepage lines emerge vertically upward. If the seepage forces are large enough to erode the soil particles, piping initiate and may progressively lead to a structural collapse. Soils which are most susceptible to piping by erosion are sands and silts. To prevent the possibility of erosion and piping, two approaches are normally used. Control of seepage and seepage forces is one approach, and the use of protective filters is the second. Certain measures, such as providing a cutoff wall or a trench to stop seepage and lengthening the flow path with the help of impervious blanket, falls into the first category. The second approach is use of protective filters which prevents erosion and reduces uplift pressure. When seepage water flow from a soil with a relatively fine grains into a coarser material, there is a danger that the fine soil particles may wash away into the coarse material. Over a period of time, this process may clog the void spaces in the coarser material. Hence, the grain size distribution of the coarse material should be properly manipulated to avoid this situation. Filter drains are required on the downstream sides of hydraulic structures. For proper selection of the filter material, two conditions should be kept in mind. The first is the size of the voids in the filter material should be small enough to hold the larger particles of the protected material in place. And the second is the filter material should have a high hydraulic conductivity to ensure the free drainage of water entering the filter and prevent buildup of large seepage forces and hydrostatic pressures in the filters. Filters used to control seepage must satisfy certain fundamental requirements. Terzaghi laid down certain criteria for protective filters. These criteria are based primarily on the grain size distribution of the filter materials and the protected materials. There are three criteria required for a good filter, which are D15 of filter by D85 of protected material should less than 5. The ratio of D15 of filter and D15 of protected material should lies between 4 and 20. And the last specification is D50 of filter particle divided by D50 of protected material should less than 25. D15, D50 and D85 refers to the particle sizes from the grain size distribution curves. Geotextiles and geofabrics have also been recently introduced as filtered with great success. So, in this chapter, we studied Laplace equation of continuity and its application in solving problems related to seepage calculation. The continuity equation is the fundamental basis on which the concept of drawing flow nets is derived. Flow nets are very powerful tools for calculation of seepage as well as uplift pressure under various hydraulic structure. The principle of designing a protective filter have also been studied in this chapter. Now I am wrapping up this lecture. Thank you.